Okay, hi guys. So today I'm just going to discuss something about voids. Okay, a void is any empty space that comes into existence when we try to arrange spheres or particles or constituents, atoms, ions, molecules, whatever the crystal is made of. We try to arrange it in a crystal lattice, then the empty space that is left inside the lattice is called a void. Now for a systematic study, we divide crystal lattice into a primitive, into a unit cell, and we study the unit cell. We study the number of voids inside a unit cell, and that's all that we require for calculation purposes. But here we'll just try to understand in this video what actually tetrahedral and octahedral voids are. So we know that the empty space which results while arranging the particles in a crystal lattice is called a void, and in the three-dimensional arrangement there are two kinds of voids: tetrahedral voids and octahedral voids. By definition, a tetrahedral void is an empty space which comes into existence when three spheres are placed in one plane and a fourth sphere is placed just above them in such a way that when we join the centers of all the spheres, we get a regular tetrahedron. Now I'll explain that. Suppose you have a sphere. Okay, now there are three spheres which are touching each other and they lie in the same plane. So it'll be something like this, and here is the third sphere. Okay, it's trying to run away. Just touching each other. Okay, and now you have a fourth sphere, a sphere which is similar in size, because we are considering a regular tetrahedron. Like, this is sort of an ideal situation. So here is the fourth sphere, and now I'm going to place it over these three spheres in such a way that when I'll join the centers of these four spheres, I'll get a regular tetrahedron. So for that, I'll first place it in the top view and then I'll lift it up like this. Now let's see what we have. Okay, and these were the three spheres. It still needs a little bit alignment. Just touching each other, not overlapping. Yeah. Now this space right here, it's empty. Okay, and this is the tetrahedral void, which is formed by three spheres in one plane and one sphere placed right over it. Now let's see if the centers of these spheres really do form a tetrahedron. Okay, now I'll do everything in front of you so that you can see. It'll be clear from how a tetrahedron is going to be formed. Okay, this is when I'm joining the centers of the three spheres which were in the same plane. There's a weld button, let's make it closed. Yeah, fine. Now I'll join the centers of these spheres to the sphere lying on the top of them. Approximately the center would be here. Let's see what we are writing. Yeah. Okay, I'll just fast forward this part in the video so you don't have to wait all the way long. Let's see. Okay, so I just checked the modeling part and this is what we read after joining the centers of these spheres, and yes, it is a tetrahedron. You can see not a regular but very close to a regular tetrahedron, but in reality no crystal lattice would be perfect. Okay, so how does a tetrahedral void look like? We know that it lies in between these four spheres, but what kind of shape does it possess? Is it called a tetrahedral void because it possesses the shape of a tetrahedral? Well, let's find out. The software I'm using provides a mechanism for doing that. Let me just remove this. So I'll just insert a cube in between these four spheres and I'll cut out this intersection of the cube and the sphere, and whatever I'll be left with will be the shape of that tetrahedron. This is the basic idea of what I'm going to do right now. So I've got my cube. It's a cuboid in fact. Works for me. I've got it in position as well. So now let's start cutting out the spheres. Okay. There goes first. There goes the second. And there goes the third. This is what we get. Okay, so this is what a FCC unit cell looks like. The spheres in the pink are the ones located at the vertices or at the corners, while the ones in the red are the ones located at the face centers. Okay, so if effective number of atoms, if we assume the spheres to be atoms, so effective number of atoms in a FCC unit cell is 4. Okay, so now where in this unit cell are we going to find a tetrahedral void? Now, from what we have done till now, okay, first let's have a look at this. It's symmetrical. No matter which face you look, you'll just get the same look from everywhere. Okay, the question is, where in this unit cell are we going to find a tetrahedral void? Now, from what we have done till now, we know that a tetrahedral void is located at the intersection of four spheres which are arranged like this, three in one plane and one just above them, so that if I join the centers, I get a tetrahedron. Now let's get back to the unit cell. Now where can I find that kind of an arrangement in this unit cell? So suppose I pick up these three, that is two vertices, two corners and one face center. So can I assume them to be similar to the to the three spheres which I chose earlier in order to get a tetrahedron, the three spheres which lied in the same plane? And the answer is no, because these vertices, they are not touching each other. So in order to select those three spheres, I need to get three spheres in this unit cell which touch each other. So that's only possible if I select three of these. Yeah, they touch each other. That is three of the atoms, or the three of the particles, or three spheres which are located at the face centers. They are touching each other, so they can be thought of as the three spheres which lying right here, just below this sphere. So I can think of these three spheres just like these three spheres which are lying below this sphere. So if I am considering these three face-centered spheres to be lying in the same plane, then the one lying above them, that is this vertex, the sphere at this vertex will play the role of the sphere uh, that lies on the top of the three spheres. So these four, if I select these four spheres, then I can say with 100% surety that there exists a tetrahedral void in between them, because again, if I join, I can show that. If you want to know, just I'll make a video that if I join the center of four of these spheres, I'll get a regular tetrahedron. Well, so now if I let me select these four spheres and give them a different color, so we can distinguish them from rest of the spheres present in the unit cell. So this corner sphere was the one which was placed at the top of these three spheres which are lying at the face center. So let's make them yellow. So now I can say that a tetrahedral void lies in between these four spheres. Now how many such similar selections can I make? Well, okay, so this is a FCC unit cell. Now if I select this corner sphere, then I can always find three other spheres which are located at the face centers, such that I get a geometry which is similar to this arrangement. For example, for this corner sphere, I can have this one at the face center, this one at the face center, and the third one will be right here. Let me rotate this. Okay, yeah. Third, the third sphere, which I considered lying in the plane, is this one. This corner sphere is the top one. This 1, 2 and 3, they are the face centers, which we have assumed are lying in the same plane. So let's make them green. So now I'll get a tetrahedral void where these four spheres meet. In between these four spheres there's a space in the 3D coordinates where no particle exists, which is completely empty, which is unoccupied. So similarly we can see for every corner that we select, for every corner sphere that we select, we can always pick up 3 other spheres which lie at the face centers, such that we get a tetrahedral void at their intersection. So since there are 8 spheres located at the corners, so in a FCC there are 8 tetrahedral voids, one corresponding to each corner sphere. So this concludes everything about tetrahedral voids as of now, and I hope this tutorial helped. Peace out.